Hello everyone, I am Meenakshi Chauhan and in this video I am going to discuss about stack organization. In this video I will be discussing about what is a stack, what are the various operations performed on a stack, what are the different types of a stack, what are the various application of a stack in computer organization and architecture. For example, as you can see in the image here, a stack of 4 books is given, showing that one end as a top of the stack which is accessible and the other end as a bottom of the stack which is inaccessible. Whenever we want to pick a book from this stack, we always pick the topmost book from the stack. Whenever we want to put a new book into this stack, we always put it onto the top of the stack. So with the formal definition, a stack is a list of data elements, or we can say data items, data objects, memory words, registers. So stack is a list of data elements, usually words, with the accessing restriction. And what is that accessing restriction? Is that elements can be added or removed at one end of the list only. And this end is called the top of the stack. The other end is called the bottom of stack. So we can access the elements of a stack from one end only, that is top of the stack. With this restriction, we can say that stack follows principle of last in first out, LIFO. The last data item placed on the stack is the first one removed when retrieval begins. The last element inserted into the stack will be fetched first. Or in another word, we can say that stack works on principle of philo, first in, last out. The element which was inserted first in the stack will be removed from the stack in the last. And the structure is sometimes referred to as a push down stack too. Now, how to work with the stack? In this, we will study various operations of a stack. Operations on a stack can be push. Push operation is to insert an element into the stack. That is, the insertion of an element into the stack is called push operation. The pop operation, to remove the top element from the stack, or removal of an element from the stack, is called pop operation. Here, every time we are working with the topmost element of the stack, so we should have some mechanism to keep the track of a topmost element of the stack. So we use a register called stack pointer. A register is used to store address of the topmost element of the stack, that is stack pointer. Stack pointer register contains a binary number, because a digital computer processes the binary data, so every information is represented in binary form. So register also stores binary information. The stack pointer contains a binary number whose value is equal to the address of the word. It will store the binary equivalent of the address of the topmost element. Now, what are the types of stack available in computer organization and architecture? There are two types of stack. One is register stack, second is memory stack. A register stack can be placed in a portion of a large memory, or it can be organized as a collection of a finite number of memory words or registers. For register stack, a finite number of registers or memory words are taken to form a register stack. For example, here a register stack of 64 words or registers has been shown in this figure. For register stack, we have taken 64 registers. starting from register 0 to register 63. And for implementing this register stack, we are using some registers such as full, empty, stack pointer, data register. Full and empty are status register. These registers describe the status of register stack, whether the register stack is full or empty at particular point. Initially, there is no element in this stack, so we can say stack is not full. Full register will hold bit 0, denoting that stack is not full. Empty is holding bit 1, denoting that stack is empty. Initially, stack pointer is pointing to location 0. So full is a 1-bit flag register for showing the status of stack, whether stack is full or not. Full means it is containing all 64 elements. Empty is also 1-bit flag register for showing that status of stack, whether it is empty, it means containing no element at all, or it is empty or not. Data register is the data register that holds the binary data to be written into or read out of the stack. It will hold the data. As full or empty, full and empty registers are 1-bit registers, so they can have either 0 bit or 1 bit. So if full is holding 0 bit, it denotes stack is not full. If full register holding 1 bit, then it denotes that stack is full. Empty is holding 0 bit, then it is denoting that stack is not empty. Empty holding bit 1 denotes stack is empty. So now to implement a register stack, we will perform some element insertion or deletion. So first we will learn how to insert an element into a register stack. First step is to increment the stack pointer. In push operation, first of all, the stack pointer will be incremented by 1. The next step is to write the item on the top of the stack. So for this, we will copy the data from data register to the stack location pointed by the stack pointer. Next, we will check the stack full condition. After making insertion, we will check whether the stack has become full or not. If stack pointer is again pointing to 0 after making insertion, we can say that the stack has become full. For that, we will set the full flag register to 1. After making insertion, the stack will no more empty, so we will assign 0 to empty register. For in a push operation, first of all, we will increment the stack pointer, then we will copy the data into the stack. Next, we will check the full condition of the stack, and next we will reset empty to 0. Now we will take an example to add an element A to the stack. Initially we have full equals to 0, empty equals to 1, stack pointer equals to 0. Full equals to 0 is denoting that stack is not full. Empty equals to 1 denoting that stack is empty, there is no element, and initially stack pointer will point to 0. To push an element, first we will increment the stack pointer. Now stack pointer will point to 1. We will copy the data from data register to the stack, or we can say we will copy element A into stack at address 1. Now we will check whether the stack pointer is pointing to 0. No. because stack pointer is pointing to 1. So this condition will fail. Now we will make empty equals to 0. As you can see in this image that A has been written at the address 1. Stack pointer is pointing to 1 and full register holding 0, empty register holding 0. Next, add an element B to the stack. Now, after previous example, we have full equals to 0, empty equals to 0 and stack pointer is pointing to 1. Now, to push element B into the stack, first we will increment a stack pointer. Now, stack pointer will point to address 2. Now, we will copy element B at address 2. We will check the full condition. Whether SP is pointing to 0? No, it is pointing to address 2. So, this condition will fail. We will make empty equals to 0. As you can see in this figure that B has been written at address 2. Now, for example, we will add one more element C to the stack. Given full equals to 0, empty equals to 0, stack pointer is pointing to 2. First, we will increment the stack pointer. Now it is pointing to 3. Data will be copied to stack. C will be copied at address 3. SP is pointing to 0. No. So condition fails. Now empty will hold 0. As you can see here, C has been written at address 3 and it is the topmost element in the stack because we can access the element of the stack by only stack pointer. Now we will learn how to remove an element from the stack. Pop operation. The first step is to read the data from the stack. So the data from the stack will be copied into data register. Now next step is to decrement the stack pointer. We will decrement the stack pointer by 1. Now after making removal of an element, we will check empty condition of the stack, whether the stack has become empty or not. For this, we will check again if stack pointer is pointing to 0, the stack will be empty. After making one removal, the stack will no more be full. For implementing pop operation, we should follow these steps. The top element is read from the stack into data register. The stack pointer is then decremented and if the stack pointer points to 0, then the stack is empty. So we will take an example. From previous example, we have inserted 3 element C at the top. So we have full equals to 0, empty equals to 0, stack pointer is pointing to 3. Now to remove an element, first we will read the data. We will read element C into data register. Then we will decrement the stack pointer. Now stack pointer will point to address 2. We will check empty condition, whether the stack pointer is pointing to 0. No. So condition fails here. Now we will assign 0 to full, denoting that stack is not full. As you can see here, now the C has been read from the stack and now stack pointer is pointing to address 2. Physically, C will not be removed from the stack. In the pop operation, no element will be removed from the stack physically, but logically it is not the part of the stack because we can access all the element of the stack from stack pointer only, and now stack pointer is pointing address 2. So we cannot access the address 3 here. Whenever we will make an insertion, then insertion will be done at address 3. So by default, the next insertion will override the element C. Some important points from the last discussion are: the first element in the register stack will always be stored at address 1. The second last element will be stored at address 63, and the last element will be stored at address 0. Now the question comes: when the second last element is inserted, then next last element will be inserted at 0 location. So how the stack pointer will move to 63 to address 0. And the same concept applies here for deletion. When the last element is deleted from the address 0, then how stack pointer will move to address 63. Now we will see how this pointer movement is done. So stack pointer movement. First we will study how a stack pointer will move from 63 to 0. The stack pointer is pointing to 63. Now 63 will be incremented by 1. We will add 1 to it. Now we will perform binary addition here. So 1 plus 1, sum is 0, carry is 1. Next 1 plus 1, sum is 0, carry is 1. Next 1 plus 1, sum is 0, carry is 1. Next sum is 0, carry is 1. Sum is 0, carry is 1. Sum is 0, carry is 1. And this result will be 7-bit answer. So stack pointer can store only 6 bits because 6 bits are used to represent 64 values. 2 to the power 6 equals to 64. So SP can hold only 60, the 1 will be discarded. So SP will hold 0 as an address. Now we will understand the stack pointer movement from 0 to 63. Here stack pointer is holding 0. Now 0 will be represented in 6-bit representation. 1 will be decremented by stack pointer. So stack pointer equals to stack pointer minus 1. But this subtraction will be performed in form of stack pointer equals to stack pointer plus or minus 1. Now minus 1, negative numbers are represented in form of 2's complement in digital system. So we will calculate the 2's complement of 1 to represent minus 1. So minus 1 equals to 2's complement of 1. So how do we calculate 2's complement of 1? We have plus 1 representation 0, 0, 0, 0, 0, 1. First, we will calculate the 1's complement to get the 2's complement of 1. For 1's complement, we will flip the bit. Flip the bit means if 1 is there, we will make it 0. Then 0 will be make it as 1. So 0, 1. Now we will have 1, 1, 1, 1, 1, 0, 1's complement of 0, 0, 0, 0, 0, 1. Now we have 1's complement of plus 1 and then we will add 1 to it to get 2's complement of plus 1. Now the minus 1 is represented as 6 ones. SP will be updated as SP plus minus 1. SP is represented by 6 0, minus 1 is represented by 6 ones. We will add these. Then the addition will result in 6 1, which is equivalent to 6-bit representation of 63. So SP is holding initially 0, and now 1 will be decremented from SP. Minus 1 will be represented in 2's complement of 1. Now we will calculate the 2's complement of 1. First we will calculate the 1's complement of 1, and then we will add 1 to it to get the 2's complement of 1. So minus 1 is represented by 6 ones. SP will be updated by addition because minus 1 has been represented in 2's complement. Then we will perform addition, then we will get 63 in binary notation. In this way, stack pointer will move from 0 to 63 after deletion of last element. Now, we will study about what is memory stack. The implementation of a stack in CPU is done by assigning a portion of memory to stack operation and using a processor register as a stack pointer. Operating system assigns memory to each program in segments. There are 3 segments in which memory is allocated to a program. These segments are program, data, and stack. So memory stack is implemented in memory as a segment assigned to a program by the operating system. The program section is accessed by a register called program counter. Program counter always stores the address of the next instruction to be fetched. Data. Here address register is used to access the data from the memory. Address register stores the address of the data which is accessed from the memory, or the data is going to be written into the memory. Here stack pointer is the register which is used to implement the stack in memory. In memory stack, a portion of memory is assigned to a program to work as a stack. Program counter, as I said, points to the address of the next instruction in the program. Address register points to the array of the data, and stack pointer points to the top of the stack. In this example, we have taken a stack starting from address 4001 till address 3000. Now we will perform some push and pop operation on this stack. Push operation. A new item is inserted with the push operation following these steps. First, stack pointer is decremented because the stack is going from higher address to lower address. So the top stack pointer moves from higher address to lower address. So we have to decrement the stack pointer in this case. Now data will be copied from data register to stack. Now for deletion, a new item is deleted with the pop operation as follows. First, the data will be read from the stack, then stack pointer will be incremented. Because in deletion, the stack will grow from lower address to higher address. Now, what are the application of a stack? One is subroutine calls. You will study in further lectures that stack is used to implement subroutine calls. Stack is also used to implement zero address instruction. It is also used to infix notation to postfix notation conversion, and it is also used to evaluate arithmetic expressions. And these will be studied in further units of computer organization and architecture. So far, we have studied about introduction of stack, various operations performed on stack, some requirement to implement, or we can say some registers used to implement stack, and various types of stacks, and the application of stack in computer organization. Happy learning. See you in the next lecture. Thank you very much.